Hello friends, welcome to Electronic Circuit Hub. So today we are going to understand about the thermal design of MOSFET. Let us say you want to design a converter, you want to design a buck converter wherein you want to understand the thermal performance of your MOSFET, the thermal performance of your MOSFET. So today we are going to understand about the thermal aspect of the MOSFET or the thermal calculation for the MOSFET. Okay. So, so in order to understand the thermal performance, let us say you have given your MOSFET is dissipating the 100 watt of power. That means the power dissipation of your MOSFET is 100 watt. The first parameter they have given is the power dissipation of the MOSFET, which is 100 watt, which is 100 watt. If you look at here, and R theta JC junction to case thermal resistance of MOSFET is 0.5 kW Kelvin per watt, 0.5 kW, and the R theta CS is 0.2 Kelvin per watt. So R theta CS is thermal resistance for case to sink. JC stands for thermal resistance of junction to case, and the CS stands for thermal resistance of case to sink. So the thermal resistance of case to sink is 0.2 Kelvin per watt, and R theta SA. R theta SA is nothing but the thermal resistance of sink to ambient. So basically, in order to design the heat sink, what you need to understand is R theta SA. R theta, usually we calculate the value of R theta SA in order to design the heatsink or in order to select the heatsink. Okay, so your R theta SA value is 1K Kelvin per watt, 1K per watt, and your ambient temperature is 40 degrees centigrade. Let us say you want to operate your product, you want to operate your MOSFET at 40 degrees centigrade. So TA is 40 degrees centigrade. Now what you need to find out it, you have to calculate the value of TJ. What is TJ? TJ is the junction temperature of your MOSFET. How much temperature is being raised in your MOSFET junction. So we want to calculate the junction temperature of the MOSFET, that is TJ, and which would be in degrees Celsius. So I want to calculate the TJ value for this given parameter, and let us say if your R theta SA means the sink to ambient thermal resistance is reduced by 50%, what is my new TJ? If the thermal resistance is being reduced by 50%, what is my new TJ? So your thermal resistance is 1K per watt. Now I want to reduce this thermal resistance to 0.5 K per watt. In this case, what is going to be my junction temperature? So we want to calculate first the junction temperature as it is for this given parameter, and then later I want to also reduce this junction temperature, this sink to ambient thermal resistance by 50%, R theta SA by 50%. So what is my new junction temperature? And we want to finally understand that whether the junction temperature is meeting our MOSFET junction temperature, which is given in the data sheet, or that junction temperature, the temperature rise above ambient is enough for my design. So let us first calculate it, and then further we talk about this. Okay, so so what is, if I have to write it, R theta, let me write it R theta JA, R theta JA. Junction to ambient thermal resistance is nothing but R theta JC junction to case plus R theta CS case to ambient plus R theta SA sink to ambient. Power dissipation, that is PD, is given by the temperature rise. I can write it delta divide by R theta JA. Okay, so you can write it, your PD is nothing but the temperature rise per degree centigrade per watt is R theta JC plus R theta CS R theta CS plus R theta SA. So what is your R theta? If I have to write it, the different parameters here, how I'm gonna write it. So what is R theta? R theta JA is nothing but the resistance resistance of junction to ambient junction to ambient. AMB stands for ambient. What about R theta JC? This is junction to case, thermal resistance of junction to case. What is R theta CS? That is thermal resistance of case to sink. Okay. And what is R theta SA? R theta SA is the thermal resistance of sink to ambient. Sink to ambient. So we know all the three values. We know R theta JC, we know R theta CS, we know R theta SA. So if I have to plug in the value, so what is my PD? Then PD is going to be delta T divided by PD you have given. They have given the PD. What is PD? So PD is nothing but 100 watt. The power dissipation is 100 watt. Delta T divided by what is the value they have given. So now I want to plug those value here. So 100 watt is the power dissipation, that is PD, and I want to calculate the temperature rise, and they have given the value of uh, thermal resistance. So this is 0.5 K per watt, and this is 0.2 K per watt, and this is 1 K per watt. Delta T is nothing but you have to multiply 100 watt multiply by 0.5, 0.7 and 1.7 degree centigrade per watt or Kelvin per watt or degree centigrade per watt, and I want to cancel out watt, and now you have to multiply delta T equals to 100 into 1.7 degree, and if I multiply 100 into 1.7, it is going to be how much? 100 into 1.7. So 100 into 1.7 is going to give you 170. So your temperature rise is 170. How much value you are getting is delta T is 170. Delta T is nothing but delta T I am getting here 170 degrees centigrade, right? 170 degrees centigrade. Now you have to calculate the junction temperature. So how you gonna calculate the junction temperature is very interesting. To calculate the junction temperature, and let me write the equation for the junction temperature Tj, and Tj is nothing but your delta T plus delta T temperature rise plus T ambient. Okay, so what is your delta T? Delta T is 170 degrees centigrade plus T ambient is 40 degrees centigrade. So what is your Tj? So your Tj is nothing but 210 degrees centigrade. Can you imagine the MOSFET you have selected is dissipating 100 watt of power, and if you want to calculate the junction temperature, okay, the maximum junction temperature of the MOSFET, which is 210 degrees centigrade, and what is your temperature rise? Temperature rise in MOSFET due to the heat dissipation or the power dissipation is 170 degree, and then you have to add 40 degree your ambient temperature. So the total worst case junction temperature is going to be 210 degrees centigrade. Okay, so now can you think of, you have to select the MOSFET which will withstand this junction temperature. So maximum what is the junction temperature of the MOSFET is around 150 degree. In datasheet, if you go and select the MOSFET, you will find the MOSFET which is rated for 150 degree junction temperature, or sometimes for automotive grade you can also find the part which is rated for 175 degrees centigrade. Now if you don't use heatsink here, if you don't control your junction temperature of the MOSFET, there will be a thermal runaway in your MOSFET and your MOSFET is going to damage. So this is the answer of my first question. What was the first question? First question was to calculate the junction temperature, and here I am getting now it is 210 degrees centigrade. Now what they are saying is, now you need to reduce the R theta SA value. So currently what is my R theta SA value? R theta SA sink to ambient is 1 Kelvin per watt, and I have to reduce this by 50%. Okay, so my R theta SA new equals to R theta SA, you can write new R theta SA equals to 0.5 Kelvin per watt. Now again I have to calculate the junction temperature. So let me write straight away the formula for junction temperature. So Tj equals to PD 100 watt multiply by your thermal resistance, which is 0.5 watt and 0.2 watt and 0.5 watt. These are the thermal resistance Kelvin per watt, not watt. Let me write it here, Kelvin per watt, plus you have to add the TA ambient temperature, and what is your ambient temperature is 40. So if I have to calculate again, so 100 watt multiply by 1.2 Kelvin per watt and plus 40 degree. So if I do math again, so this will become I do not need to use calculator. So this will become is 120 degree centigrade, and this will become 40 degree centigrade. So your Tj new, I have to write it here. The new junction temperature is Tj new, and the value of Tj new is 160 degree centigrade. Now you have reduced the sink to ambient thermal resistance, which is R theta SA. Okay, you have used, let's say, convection cooling technique. You have used a force cooling, and you have used a fan, and after using the fan you have reduced the thermal resistance value for sink to ambient. Even then you got the temperature, earlier it was 210 degrees centigrade, now the junction temperature Tj new is 160 degree centigrade. Now this is still not enough. You have to work around somewhere the MOSFET junction temperature around 100 degrees centigrade. You have to further reduce your sink to ambient thermal resistance. In order to reduce the temperature, you have to reduce further uh, thermal resistance of your sink to ambient. This is still not recommended. You cannot use 160 degree junction temperature of your MOSFET. So your answer of your second question is, what is the answer here I'm getting? So it is, the second question answer is 160 degree centigrade. Okay, the first question answer is 210 and the second question answer is 160 degree centigrade. Now what you need to understand is, you have got, even reducing the thermal resistance, you have got 160 degree. Okay, and that is how you can understand and you can analyze the thermal aspect or the thermal performance of your MOSFET. Okay, and that is how you're gonna design the heatsink. What is the PD in the MOSFET? They have given 100 watt. In case if they have not given 100 watt, the power dissipation of the MOSFET is not 100 watt. How you gonna do that is, you have to calculate then the conduction loss of the MOSFET and the switching loss of the MOSFET. By calculating the conduction loss and the switching loss, you can calculate the power dissipation. Once you get the power dissipation, then you have to follow these steps to calculate the junction temperature. Okay, so hope guys you have understood now the thermal design of the MOSFET, the thermal aspect of your MOSFET for your converter design. If you have still any question on this calculation, feel free to ask me in comment section, and thank you so much for watching this video.